So this envelope form here valid for maximum shear stress theory. So this one is for maximum shear stress theory, MSST. And for brittle material, we are using maximum principal stress theory. In that case, we have assumed the value of SUC greater than the value of SUT. But if you assume the value of SUC is equal to SUT and you apply the maximum principal stress theory, we also know that the value of SUC is same as equal to SYC and the value of SUT is equal to SYT. So if I assume such condition that, so this is just to compare the two theory, that is for brittle material and for ductile material. In that case, if I draw the MPST, then this region is remain same. We will get here another rectangle or another square because we have taken the value of SYT is equal to SYC. And we'll get here another rectangle or another square like this one. So this dotted line represent here the maximum principal stress theory. So as far as quadrant 1 is considered and the quadrant 3 is considered, both theory will give the same result. Because the boundary form in the case of MSST and MPST, that is this one is same as equal to MPST. In quadrant 1, both theory has the same fence. Even the quadrant 3, they have the same fence. Therefore, the factor of safety for quadrant 1 and quadrant 3 by MPST and by MSST give the same value of factor of safety. If we have a principal stress sigma A and sigma B are in this region, in this zone, let's say here we have point A or here in point B, that is in the quadrant 2 and quadrant 4. I have taken the 2 points, one is A and other is B. For this one, we find here that this point is inside the MPST. Point A is within the MPST limit, so part will not fail. But this part is outside the MSST, so part will fail at A. Similar is true for B. This B is inside the MPST boundary, so part is not fail. But according to MSST, the part will fail. That is, if you consider the 2 points in the quadrant 2 and quadrant 4, that is point A and point B, in that case, the factor of safety using the MPST and the factor of safety using MSST will be different. It will fail according to MSST. It means that the value of factor of safety for MSST will be less than 1. And it is not failed by MPST, so factor of safety will be greater than 1. When it is not fail, it means that the factor of safety is greater than 1, and if it is fail, means the factor of safety is less than 1. So these are the few observations about the MPST and MSST, that is the maximum principal stress theory and the maximum shear stress theory. Let me explain you why if we select a point here, that is the point A, which is very much is satisfied according to maximum principal stress theory and the part is safe. But according to the maximum shear stress theory, the point A is outside the fence and therefore it will fail. So as far as the point A is considered, we have sigma A is equal to minus 180 and sigma B is equal to plus 180. So we have sigma A is equal to minus 180 and we have sigma B is equal to plus 180. And we are given the value of SYT is same as equal to SUT is equal to 240 and SUC is equal to SYC is equal to 240. That is just we want to compare here that if the point A, the part will be okay according to MPST but part will fail according to MSST. One value of sigma A is minus 180, other principal stress equal to 180, that is a positive value. So this value will assign as equal to sigma 1, this value will assign as sigma 3 and we'll make the value of sigma 2 equal to 0. So in this case the maximum value of the shear stress but absolute value is always given by sigma 1 minus sigma 3 divided by 2 and is same as equal to SYT divided by 2 divided by factor of safety. And this one is our MSST, that is a maximum shear stress theory. Sigma 1 minus sigma 3 divided by 2, and these two will be get cancelled. So we have sigma 1 minus sigma 3 is equal to SYT divided by the factor of safety. So let's call it as factor of safety 1 for MSST. We have sigma 1 is equal to plus 180. Minus of sigma 3 is equal to minus 180. And we have SYT is equal to 240 divided by factor of safety for MSST. Factor of safety for MSST is equal to 240 divided by 360 is 0.666, is less than 1, and therefore the part will fail. But if you apply the condition for MPST, and since the boundary is same for quadrant 2, so in this case the out of sigma A and sigma B both are identical value, so this time we have sigma B is same as equal to absolute value of sigma A is equal to 180 megapascal, and we have factor of safety we can write as SUT or SYT divided by maximum principal stress. So they are identical, so we can write any value. SUT is equal to 240 divided by 180. So 240 divided by 180 is 1.33. If you have a factor of safety is greater than 1, means the design is safe. So if you have a machine part whose principal stresses are as indicated by A is equal to sigma A is equal to minus 180 and sigma B is equal to plus 180. This is just an example. Then we are in the quadrant 2 and the part will fail according to MSST and the part is safe according to MPST. Because the factor of safety in the case of MSST is less than 1 and for MPST the factor of safety is greater than 1. This time we take the second case. We are still in a second quadrant and we are these principal stresses. That is at point A, we have 60 megapascal compressive and sigma B is equal to 120 tensile. And we will check here what is the factor of safety given by MSST and MPST. So we can read this value. We have sigma B value is equal to 120 tensile and sigma A value is equal to 60 compressive. So in this case we have sigma A is equal to minus 60 and we have sigma B is equal to plus 120. So the higher value will assign to principal stress 1 and the least value will assign to sigma 3. Then the value of sigma 2 will take equal to 0. So let's calculate here again. Tau max absolute value is same as equal to sigma 1 minus sigma 3 divided by 2 is same as equal to SYT divided by 2 times of factor of safety. So 2 and 2 cancel. We have sigma 1 minus sigma 3 is same as equal to SYT divided by factor of safety. Sigma 1 is equal to plus 120 minus sigma 3 is minus 60 equal to SYT, and this time we have SYT is equal to 240 divided by factor of safety. So factor of safety according to maximum shear stress theory will be equal to 240 and we have plus 180 is equal to 1.33. 1.33 is greater than 1 because we have selected the point A within the fence of MSST. So the part is safe. No doubt the part is safe. And in the case of MPST, since here the boundary is same, so you have to select the maximum value of this. So in this case we have sigma V is greater than the absolute value of sigma A. 120 is greater than 60, so design is based on sigma B, and we have factor of safety for MPST will be equal to SYT. All these values are same, so we are writing here SYT or SUT, doesn't matter, divided by sigma B. Sigma B is the largest principal stress. So we have SYT is equal to 240 and sigma b will be equal to 120. What we observed here is that we are getting the higher value of factor of safety. So if the point is lying inside the region, maximum shear stress theory always give the less value of factor of safety, because this distance is a smaller distance as compared to this distance if I join the load line with the origin. So what we observed here is that the factor of safety in the case of maximum principal stress theory is greater than the factor of safety in the case of MSST. But in this region they are the one and the same value. So in quadrant 1 and quadrant 3 you will get the same factor of safety because the fence is same. Only the problem arises in the quadrant 2 and the quadrant 4. In quadrant 2 and quadrant 4 it really matter if you are here, then the part is safe according to maximum principal stress theory, but the part will fail maximum shear stress theory. But if you are inside this region, then the part is safe by both the theory, but the factor of safety according to maximum shear stress theory will be less, and the maximum principal stress theory it will be the higher value. Suppose we have both the principal stresses sigma A and sigma B are positive, or both the principal stress are negative. In that case the factor of safety given by the maximum shear stress theory MSST and the maximum principal stress theory MPST, they are one and same. To prove this, we'll take this point equal to A, and this time we have the value of sigma A is positive 120 and sigma B is equal to positive 180. So we have sigma A is equal to positive value is 120, sigma B is equal to positive value 180. So both the value are positive, so higher value you have to assign equal to sigma 1. This value will assign equal to sigma 2, and the third value in this case will be equal to 0. That is the value of sigma 3 will be equal to 0. So if we apply the maximum shear stress theory, in that case we have tau max absolute value, which is given as sigma 1 minus sigma 3 divided by 2. This relation is fixed. Only thing that you have to arrange the value of sigma 1 greater than sigma 2 greater than sigma 3, and this will change every time. This value is same as equal to SYT divided by 2 by factor of safety 1. So 2 and 2 will get cancelled. We have sigma 1 minus sigma 3 is equal to SYT divided by factor of safety. So factor of safety here for maximum shear stress theory will be equal to SYT, that is equal to 240. We have value of sigma 1 is equal to 180, the largest value, and the minimum value is 0. So we have 240 divided by 180 is 1.33, and the part is safe. Now we'll apply here maximum principal stress theory. So for maximum principal stress theory, for quadrant 1 we have same boundary, that is SUT or SYT, and maximum principal stress here is sigma B. So in this case sigma B is greater than sigma A. So factor of safety according to MPST will be equal to SYT or SUT, which is same as SYT. Largest principal stress here is sigma B. This guarantee the lowest value out of these two will be equal to 240, and sigma B is same as equal to 180. So this gives the same answer, that equal to 1.33. So for quadrant 1 and quadrant 3 we can have the same result, that both the factor of safety given by maximum principal stress theory and the maximum shear stress theory are identical. Only for quadrant 2 and quadrant 4 they are the different value, and sometimes the part will fail if you are this region in the quadrant 2, but inside this region, that is within the boundary of MSST, the part will not fail. That is a safe design. And one last fact about the maximum shear stress theory. This theory does not hold good for hydrostatic stress. Hydrostatic stress means that the stress acting on the three-dimensional element is equal in magnitude in all the direction. Either it can be compressive in nature or can be tensile in nature. This time the value of sigma x will be same as equal to sigma. Value of sigma y is also equal to sigma, and sigma z is also equal to sigma. So when we say the magnitude and the nature of the three stresses along the x, y, z are identical, then it will be called as hydrostatic stress. In the MSST, you have to arrange the stresses in the order of sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. And this time sigma 1 and sigma 2 and sigma 3, they are the same value is equal to sigma. If the shear stress is not acting on the plane, then that plane will be representing the maximum plane and the corresponding value will be maximum principal stress. So if you try to construct the Mohs circle with sigma 1 and sigma 2, it will be point. Sigma 2 and sigma 3, it will be also point, and sigma 1 and sigma 3, it will be also represented by a point. So let's say we have sigma axis and this one is tau axis. This time all the values are positive. So this value represents the sigma 1 as well as sigma 2 is equal to sigma 3. So Mohs circle is a point here, and the radius r, which is representing the value of tau max, or we can say tau max absolute, they are one and same and they are equal to 0. And if you are not able to define the tau max, then the maximum shear stress theory does not hold for the hydrostatic stress. So this one is an objective question may be asked in the examination. We cannot apply the maximum shear stress theory in the case of hydrostatic stress, but we can very well apply the principal stress theory. So we can very well apply the principal stress theory in the case of hydrostatic stress. And according to principal stress theory, we have any value we can select here is sigma 1 will be SUT divided by sigma 1. Will give the value of factor of safety. If you want to find out the factor of safety for hydrostatic stress, then you can solve it by using the maximum principal stress theory. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.